Okay, so today's lesson starts reflections. You kind of worked on the delta math yesterday that involved reflections over the axes. This is just the explanation of why I gave that to you yesterday, and then you're going to work a little bit on it after you watch this video. So you're going to fill in your notes as we go along. So by the end of this lesson, you're going to be able to reflect a point over the given set of axes or a set of points, so a shape. So when we think of what is a transformation, I think about thinking about real life or when transformations occur. I think about I think of the movie Transformers, where the objects are kind of like changing into these like robot looking things. So I think about a Transformers, the movie, or I think about like a transformation of a person, like a makeover, right? Those are like two real life things that I've thought about that would work in terms of real life and transformations. So you're just changing or taking something that exists and moving it, making it different. So a transformation in math is a process that manipulates a polygon, which is just a shape, or any other two-dimensional object, a set of points on a coordinate plane or coordinate system. So if we think about this triangle below, how can we take this and transform it? Well, I could take this shape, right? And I could take it and I could kind of like rotate it. Let me get my pen. So I could take this shape of this triangle and I could make the flat side kind of go up top where it would look like that. So like the Z that's in that corner would be up here. The X would be down here. The Y would be over here. So I basically just took it and rotated this, right? This would be side A, this would be side C, this would be side B if I kind of rotate it again, right? I could actually do it then again, and I could make it look like this, right? Z is now here, my X is here, my Y is here, so this is still C, this is A now, and this is B, right? So I just basically just kept rotating it. So what we did was, I'm going to type this in for you to write as well. We turned, flipped, we slid, right? That's not in the same spot, all over, but we kept the shape the same. That's what's important with this. The shape stayed the same. Right? Technically, I could even just take the shape that we started with up top, the original one, and I could just take it and I could like move it down, right? I shifted it. It's not exactly the way it was. It looks exactly the way it was, but it's shifted down. That's like a slide. I didn't really show that one before. So basically, under a transformation, the object or polygon that we started with is called our pre-image, our starting image, right? Anything after that, the transformation, is just called the image. It's the new image that we're making. So a transformation, basically, the way we can write it, so our pre-image, and I apologize for the lack of connection between all my letters here. So my pre-image I could write as triangle ABC, right? And then my new image, this is what's kind of new. You saw it in the delta yesterday, but like it could be triangle A, and we call it prime. It has a little like dash with it, B prime, and then C prime. That's how you would note a transformation and the way the new object would look. So a transformation that keeps the same size, which means that my distance doesn't change, right, in my object, and it keeps the same shape. It says distance. Keeps the same shape, which would mean the angle measures stay the same. It's called a rigid motion. Think of the word rigid, I mean like stiff. So the shape of my object is not changing at all, right? It's an isometric transformation, which just means it's of equal measure. So again, I know I kind of just wrote a lot there. Just make sure you jot some of this stuff down. It is important. So this is kind of what we did in that example where we kind of like slid something, flipped it, and turned it. The specific names of these transformations, when we slide something, it's called a translation. When we reflect it, we flip it, which is what you worked on yesterday. And when we rotate something, we turn it. Okay, these are all those transformations. So what we're going to focus on today is that middle one, that reflection. So reflections are around us every day. So 2 examples maybe in real life is, I always like when you're looking at the ground and you kind of have, or in a mirror, I should say, like a mirror, you're looking at your reflection. This image here shows a reflection of the mountain into the water, so it's reflecting. So in geometry, one of the big things we do is reflections of a line, in a line, I should say. So key thing to realize is this is my pre-image. This is what I started with. Ooh, and I'm using the same exact color. Right, this is my pre-image. And what's important to realize is that the distance from line K that we're reflecting over, right, because my new image is on the right side, this distance C and C to C prime from K is equal. These are equal distances. So I could, if it was on a grid, I could count boxes and they should equal each other. Same thing would go for from B to B. So where B was to B prime, this distance again, amount of boxes I would count would be equal to each other. They'd be equivalent. That's what these dashes are saying. And then same thing on the bottom, A to A, those would be equal distances also. And you can see the word equals below it, right? So that's all that diagram is saying. So here the notes are kind of filled in for you. So a reflection can be thought of as flipping or folding an object over this line of reflection. So you're taking the image and you're literally flipping it over. An object and its reflection have the same shape and size. So nothing is getting smaller, nothing's getting larger, but the figures do face in opposite directions. It's like looking in the mirror. They're opposite of each other. The object and its reflection are the same distance from the line. So like I said before, you could count your boxes so that you could see how far away you are from that line of reflection. So the line of reflection is the perpendicular bisector of the segment joining every point. So that they're saying in that statement is that line K is perpendicular to all those lines, those dotted lines that we're connecting the endpoints to. Also, naming, lettering the figure in a reflection requires changing the order of the letters, such as from clockwise to counterclockwise. So basically what it's saying is if you named this ABC on the left, when you name it the other way, it's flipped. So you're reversing the way you're saying it. ABC is now the opposite direction. Starts on the bottom. So by that, they're saying that this moves counterclockwise the way you read it, ABC. When you read this one, you're going backwards and you're saying it's counterclockwise, ABC. Okay, so the big thing is the way that they note this, the way they write the reflection symbols. So symbol notation is you use this little r. So it stands for reflection, and LOR just stands for the line of reflection. So for example, if I was reflecting over the x-axis, I would write it like this, with the little x, the word x-axis in little letters. If I was doing a reflection over the y-axis, I would write it like this, right? That's what this would be, this little line of reflection. So my pre-image, keep in mind, my pre-image could be a point, could be a shape, right? That's what my pre-image would be. Okay, so how to reflect a point or a set of given points over a line. So you're going to plot your first pre-image, which is that first shape. You're going to highlight or, make in a different color your line of reflection, and then you're going to take each point in your pre-image and count the number of spaces to over your line of reflection and do the same thing on the opposite side. So for example here, just to show you A, so if you look at point A, the top shape up here is my original image, right? And A was one space up from you're reflecting it over the x-axis it's telling you. So here's my x-axis. So if you wanted to, you could highlight this. Right, so I would highlight this axis. This is the axis that I'm reflecting over. So my point A is one box up from my x-axis. So if I was going in the opposite direction to plot it, this would be A prime because I'm going one away. For C, I'm going up 2. So again, on the same, number 3, I'm going down 2. So you're just making sure you're equidistant from your line of reflection. So like example 2, you're reflecting now over the y-axis. So this would be the line you would highlight. And A goes to the left one. So A goes to the right one here. To get the new image, I'm going to count 1 over on the other side. So you're just literally counting boxes. So in these, what stays the same, meaning what doesn't change. So the size of my shapes don't change. That's your distance. So the distance between each point does not change. Your angle measure does not change. That's going to be your shape, because if I reduced or made an angle greater, it would change the whole shape of my figure. Some things that do change are going to be our slopes can kind of reverse, and one can be positive, and then they could change to be negative. And then the orientation, that just means like clockwise now to counterclockwise. Oh, I spelled that wrong. So just write those down. Okay, so the next section is asking you to actually try this. So the first part basically is what you did in Delta Math already yesterday. So I feel like that part you guys can probably do on your own. So I'd like you to try 1 through 8 now. Okay, and then I want you to continue, and I want you to try the rest of this. I will go over it when I come back tomorrow, but I would like you guys to try to finish doing all those questions and see if you can do them. The delta from yesterday should also be completed by the time I come back to school tomorrow. And make sure your note packets are completed as well.